Hey Ramblers, this video is going to cover the material in chapter 7.1 in our book. It's going to talk about the sum of the measures of the angles of a triangle, something we've already proved in class. We're going to talk about a stronger form of the exterior angle theorem, and then we're going to learn the midline theorem, which is a crazy useful theorem that is kind of unexpected, and I think you're going to enjoy the proof of it. I hope you enjoy the video. It really is a great segue from quadrilaterals into polygons with more than 4 sides. So I hope this helps. Thanks for watching. Let's say that I'm given triangle ABC, and I construct a line through C that is parallel to AB. We can do that because of Euclid's fifth postulate. Now that's going to create 3 angles. Let's label those angles X, Y, and Z. Now, since AB is parallel to the line that we've drawn through C, I know that the angle at X is going to be congruent to the angle that had been at A by parallel lines imply alternate interior angles. And then angle represented by Z is going to be congruent to the angle down at B. Now notice up here at C I have 3 angles, X, Y, and Z. And we've known since the first chapter that 3 angles that form a straight line equal 180 degrees. So the 3 angles at vertex C that add up to 180 degrees also represent the 3 angles that make up the interior angles of the triangle. So the interior angles of a triangle add up to 180 degrees. Let's take a look at the next theorem. You'll recall that in chapter 5 we learned the exterior angle theorem. And that said if we extended one side of a triangle, we created an exterior angle. And that exterior angle was greater than either remote interior angle. So in other words, the exterior angle was greater than angle X, and the exterior angle was greater than angle Y. All right, we found that it was useful for determining restrictions on the values of some of the angle measures in some of the diagrams we looked at in chapter 5. But now that we know that the sum of the angles of this triangle is 180, we can present a more robust theorem. And that is the exterior angle theorem, but you'll see that it's much more useful. For now we're going to say the exterior angle of a triangle is equal to the sum of the remote interior angles. In other words, the exterior angle is equal to X plus Y. Let's quickly take a look at that proof. We know that the exterior angle plus angle Z equals 180 degrees since they form a straight angle. But we also learned in the last theorem that X plus Y plus Z, which is the sum of the interior angles, also equals 180. So if I set these two equations equal to each other, since they're both equal to 180, I see that the exterior angle plus Z equals X plus Y plus Z. So in my final step, I'm simply going to subtract Z from both sides. And when I do that, I'm left with the exterior angle equals X plus Y, which was exactly what we wanted to prove. This will be a very useful theorem as we try to develop some of the formulas that we're going to use to find angle measures throughout chapter 7. Okay, the last theorem I want to cover is called the midline theorem. And while it seems pretty specific in its use, it actually could have been presented in chapter 5 along with parallelograms, and it turns out to be really useful to us in chapter 7. But what I find most interesting is the proof. So while you don't have to memorize this or ever have to replicate it, it is interesting just to see how the proof is done. So here's what we're given. A triangle, ABC, and the midpoints of two of the sides, so midpoint H and midpoint M. And the theorem reads like this. If a line joins the midpoints of two sides of a triangle, then that line is parallel to the third side and half the length. So let's take a look at the proof. Okay, this isn't really anything we've seen before, but we're going to extend HM through M all the way to P, such that HM is congruent to MP. So this segment here will be congruent to MP. Since M is a midpoint, AM is going to also be congruent to MC. And angle AMH will be congruent to CMP because they're vertical angles. Therefore, triangle AMH here is congruent to triangle CMP by side angle side. So that makes angle A congruent to angle CMP by CPCTC. Since those two angles are alternate interior angles, I know that AB is parallel to PC. Also, AH is going to be congruent to PC by CPCTC. Since H is a midpoint, HB is also going to be congruent to PC by the transitive property. So, since I have HB parallel and congruent to PC, I know that HBC is a parallelogram. So therefore, these two sides, HM and BC, must be parallel. So the first point is proven. Now, since this is a parallelogram, and I know that HP must be congruent to BC, since HM is half of HP, HM must also be half of BC. And we've proven it. Well, you'll find that we're going to use this quite a bit as we make our way through the chapter. Okay, a lot of material here. Please feel free to pause and go back if you need to. Thanks very much for watching.